Improving traffic safety and operations is our main goal. However, traffic collisions still occur. Leaders from academia, industry, and government are working together to accelerate the deployment of advanced ITS, or Intelligent Transportation System, a type of communication technology to tackle this global challenge. We will explain V2X, or Vehicle to Everything, as a typical ITS for safety. The US, Europe, and Japan all have slogans for reducing traffic accidents, with the goal of no deaths or serious injuries. According to the U.S. Department of Transportation, the main requirements for V2X are that exchanges are non-networked, protocols are interoperable, coexistence in the same channel, and must be backward compatible. Devices are omnidirectional with 360 degrees of coverage. Communications operate predominantly within a 300-meter range. Signals are largely unaffected by environmental conditions. Also, V2X is uniquely crafted for certain crash scenarios. It can also be used in other vehicles. Communications have been designed for significant security and privacy protection, with low latency, free from harmful interference, coverage with scalability, high reliability, and stability. In the United States, the Federal Communications Commission proposed 5.850 to 5.925 GHz for ITS in 1999 and announced it in 2003, making a buffer of 5 MHz against unlicensed Wi-Fi under 5.850 GHz. V2X requires 75 MHz for U.S. road safety. This allocation includes critical V2X services, such as basic safety messages, vehicle-to-infrastructure messages, collective perception messages, maneuver coordination messages, messages for platooning and CACC, and messages for vulnerable road users, to name a few. This requirement was calculated by multiple independent sources, including SAE and C2CCC. The use of collective perception messages allows vehicles to see what they otherwise could not: further distances and around obstructions, such as curves and buildings. Connected infrastructure or a connected vehicle can spot non-connected vehicles and non-connected vulnerable road users, such as pedestrians, bicycles, scooters, motorcycles, and road workers. That information is transmitted to other vehicles whose drivers do not have a line of sight to the non-connected objects, allowing the vehicles to react ahead of time, faster than they could otherwise. This advanced warning can reduce accident frequency and potentially save lives, even when not all of the vehicles involved are connected. Maneuver coordination messages allow vehicles to know what other vehicles intend to do ahead of time. With the existing 75 MHz allocation, services using CPM and MCM may be available in the near future, with completion expected by 2022 or 2023, and U.S. deployment is expected by 2024 or 2025. However, if the NPRM, or Notice of Proposed Rulemaking Channel Plan, is implemented, this service will be lost. These channel allocations have been used to support a basic set of V2X messages that lay the groundwork for a wide range of applications that are beneficial to the public. They require the entirety of the existing 75 MHz for real-world use. What are the basic characteristics needed for V2X Basic Safety? There are often discussions focusing on communications performance, such as packet error rate and communication range, but there are other more important indicators. These 4 keywords are important for V2X Basic Safety messages. The keywords are everyone, everywhere, different generations, and scalability. V2X Basic Safety requires reliable communication with everyone. If some vehicles or infrastructures cannot communicate with each other, V2X Basic Safety services will not work. In order to communicate with all vehicles and infrastructures, interoperable technology is key for V2X Basic Safety. V2X Basic Safety requires reliable communication everywhere. Vehicles travel to various places outside of urban and residential areas where not so many infrastructures are deployed, such as mountains, or through tunnels. And V2X Basic Safety requires reliable communication with different generations. The average life of a vehicle is 12 to 15 years. So if new technologies are replaced one after another, new vehicles and old vehicles won't be able to communicate with each other, and V2X Basic Safety services will not work. In order to communicate between old vehicles and new vehicles, backward compatibility is necessary for V2X communication technology. In addition, V2X Basic Safety requires reliable communication with scalability to be able to communicate reliably even under congestion. Communication should not be lost when there's too much traffic. Communication for each vehicle must be reliable even when congested. Most importantly, communication technology must be mature for V2X Basic Safety. Mature means that the technology has been verified over many years, tested in traffic and other various scenarios. ITS communications have 2 major categories: direct communication for vehicles and infrastructure systems, called V2X, and V2N, where signals are communicated through telecommunication networks. V2N is used to connect vehicles and has been used for many years. Direct V2X communication is suitable for collision avoidance and automated driving, while network-based V2N is good for sending large amounts of data to broad areas. DSRC, Dedicated Short-Range Communication, is a V2X technology specifically developed for transportation safety applications. An appropriate mix of these 2 different technologies, V2X and V2N, is a good approach for ITS communication. This mix is sometimes called hybrid communication and has already been applied to vehicle and infrastructure systems around the world. DSRC technology for safety is developed based on well-established, stable Wi-Fi technology. There are recent proposals to use cellular technology for direct V2X communication. There may be some confusion about DSRC and Cellular V2X. Here are some things to know. DSRC is a well-established and proven technology. Its stability is a key factor for vehicles and transportation systems due to its long history and promises of future success and evolution. A misinterpretation of this stability is that it is an obsolete technology. But again, this stability is an important factor for transportation systems. DSRC is also designed to evolve into its next-generation technology, properly named NGV, or Next Generation V2X. Experts are developing this next generation of technology now under IEEE. Since NGV is an evolution of DSRC, it is designed to assure interoperability, coexistence, and backward compatibility with DSRC. NGV does not require spectrum separate from DSRC. DSRC already has a well-established ecosystem, and it will be further enhanced to evolve with NGV. By contrast, there is no interoperability, same-channel coexistence, or backward compatibility between LTE V2X and Future's NR V2X. NR V2X requires a separate spectrum from the LTE V2X. That is the reason why only DSRC and NGV have an evolution path with interoperability, same-channel coexistence, and backward compatibility. DSRC has already been implemented in Japan, Europe, and the United States. While in China, the government and private sectors are moving toward the introduction of another technology, often called Cellular V2X. But it is LTE V2X PC5 based on 3GPP Release 14. A number of pilot projects are underway in China to deploy LTE V2X and V2N applications for infotainment. V2N using a cellular technology has a good possibility for infotainment because it enables transportation authorities to monocle vehicles in a broad area to improve traffic operations. V2N, by definition, requires the use of commercial cellular networks by carriers. To start with, LTE is a voice and data communication technology. Following on from 3G and 4G, we are now starting to welcome in 5G, which features high capacity, ultra-high speeds, substantial connectivity capability, and low latency. However, it needs a dedicated infrastructure that will require enormous cost and time to build out. And the fact is that cellular networks employ base stations as translation devices between generations, but direct V2X has no such translation device. As such, places with 5G connections are limited in the early deployment phase. Various advertisements questioning whether cellular communication technology can be used for V2X are causing confusion. Adopting technology for phones that are replaced on average every 2 to 3 years differs from the adopted technology for the life cycle of vehicles, which is approximately 12 to 15 years in the US, Europe, and Japan. Established, reliable, and proven technology is necessary for cars where safety is paramount. 3GPP Release 14 specifies direct V2X communication technology based on LTE technology. However, since the US standard SAE J3161/1, which defines the minimum requirements for V2V Basic Safety messages transmission, has not yet been determined. Release 14 LTE V2X technology has not been fully tested in various scenarios and aspects, such as scalability in congested scenarios for V2X safety communications. Release 16 specifies a new radio access technology for direct V2X based on 5G technology, referred to as New Radio. The Release 16 standard was completed in June 2020. Release 17 will enhance 5G NR V2X technology. 5G NR V2X will require further standards for analysis, evaluation, and vehicle safety before it can be used on the road. For safe driving, what are the technical requirements being sought for V2X communications? One of the difficulties with V2X is that you don't know which car will need to send specific information, nor who will need to receive that information. For this reason, it's necessary to adopt technology that will allow each car to broadcast its location and speed at regular intervals, and also allow nearby cars to reliably receive that information. Let's see why DSRC is more reliable than LTE V2X. DSRC utilizes a CSMA with CA technology. Randomly, the vehicle first confirms that no other car is transmitting before sending out data. With this mechanism, typically only one car occupies the channel at a time. Thus, all surrounding vehicles are able to receive the transmission. As long as each car periodically carries out these random transmissions, the communications are achieved. DSRC is a mature technology that satisfies the V2X requirements. On the other hand, with LTE V2X PC5, the time resources are divided into 1 millisecond subframes. The frequency resources are divided into 10 subchannels. These are the resource units that cars use to communicate. Each car checks the usage status of the resource for the most recent 1 second and then randomly selects one of the resources that is in the bottom 20% of power consumption to communicate. The resource selected by each car is used every 100 milliseconds. After a resource is selected, the transmitter doesn't check to see if anyone else is transmitting before starting to transmit. The resource usage is known as semi-persistent scheduling. LTE V2X differs from DSRC in that it allows simultaneous communication among multiple cars using different subchannels, each of which repeatedly uses its same selected resource. Due to these differences, this may result in several issues. The first issue is the persistent packet collision problem. If multiple cars select the same resource, communications using that resource will repeatedly collide. The second issue is the persistent half-duplex problem. When multiple cars transmit simultaneously, even if different subchannels are used, they will not be able to hear each other while transmitting. The more subchannels that are set, the more likely it is that this issue will occur. The third issue is the persistent near-far problem. In the situation noted above, according to the positional relationship of the receiving vehicle, the strength of the signal from a nearby car will be too strong, meaning that there is a possibility it will not be able to hear the transmission from a car that is farther away. Because of these issues, LTE V2X can be unreliable due to the persistent packet loss. To combat this, packets are usually duplicated and sent twice. As a result, LTE V2X requires twice as much bandwidth as DSRC or NGV. So when traffic is congested, there is a risk that this will further exacerbate the issue. For LTE V2X PC5 to mature as a V2X communication technology, it will need to prove that communication in difficult circumstances can be established. This summary compares DSRC to LTE V2X from a safety perspective. In order to be installed in vehicles, the first priority is safety, and the V2X technology used for vehicles must be mature and reliable for V2X safety services. Let us consider V2X safety for both car manufacturers and related suppliers. In the United States, Europe, and Japan, DSRC is deployed as the only mature and proven technology for direct V2X communication because DSRC technology was developed specifically to satisfy transportation safety purposes by experts around the world. Through collaboration, DSRC technologies have already been validated for and deployed in real-world use in Japan, the United States, and Europe. Approximately 9,200 RSUs, or roadside units, have already been installed in the United States by U.S. DOT and State Departments of Transportation as of July 2020, and 12,400 units in total will be installed soon. Numbers of roadside units and infrastructure are progressing steadily in each region of the United States, Europe, and Japan. Through the continued expansion of deployed DSRC V2X technologies in Japan, Europe, and the United States, as well as continued allocation of already allocated dedicated V2X spectrum, our transportation systems will become safer and smarter while using our transportation resources more efficiently. DSRC V2X technologies have been expanding for our ultimate safety goals.